Hello everyone. In this video, I'm going to explain you what root mean square or RMS is and how we can calculate it for deterministic and non-deterministic signals. So RMS holds a monumental importance in various fields such as engineering, physics, and signal processing. And essentially RMS describes an equivalent fixed DC value for a varying quantity. Without loss of generality, let's assume this varying quantity is a voltage signal Vt. The voltage RMS would be equivalent effective DC voltage source that when connected to a resistive load, to an identical resistive load, will cause the development of identical average power over time, or same heat on a same resistive load. So here, for average power over a given time duration of delta t, we know it's gonna be energy divided by delta t, which is 1 divided by delta t integral over delta t of instantaneous power. And we know instantaneous power for a resistor would be instantaneous voltage square divided by resistance. And from this side, we know the average power is voltage RMS square divided by resistance. From these two equations, we can cross out the resistance and obtain the formula for voltage RMS, which is a square root of 1 over delta t integral of instantaneous voltage square. So this is the formula we've got for a deterministic signal. This is the formula for RMS for a deterministic signal. For non-deterministic signals, we will shortly see how we can calculate the RMS. Here there is a deterministic waveform for an arbitrary voltage signal in a specific time duration of t0 to t1. In order to obtain the RMS value, we need to do the following steps. First, we need to make a square of the signal, which represents the instantaneous power of the signal, and then we want to integrate it over the given time duration, which is equivalent to energy of the signal. We also need to divide it by the time duration, representing the average power of the signal. If you noticed, we didn't use the resistive load here because we already know it's gonna be vanished from our equations. So you can just simply assume we've got a normalized 1 ohm resistor load here. So in order to obtain the voltage RMS, we also need to take a square root of the mean square, and for a specific case when the signal is periodic, we just need to replace the time interval, the delta t, with periodic time t. So here there are some examples of RMS values for some deterministic signals. A sinusoid signal, A sine 2pt over capital T, or omega t. The voltage RMS here is A divided by the square root of 2, and as you can see, it's agnostic to the frequency. Another example here is an antipodal square wave, which can take amplitude A and minus or antipodal A. The voltage RMS here is simply like a DC voltage source with value A. And the last example is the antipodal triangle signal, which the voltage RMS is A divided by square root of 3. So not all the signals are deterministic, and RMS is a concept which is not only applied to deterministic signals, it applies to all kinds of signals, including random processes and random variables which are time sampled of random processes. So here the total power of a random process X is expectation of its square given by this formula, where the PDF is power density function of the random process, and the RMS value of the random process is a square root of the total power. So in many cases, when we discuss about random processes such as noise within a digital receiver, we would practically discuss about a noise process with zero mean. Just as a side remark, when we have a random process with non-zero mean, like this example here, the random process can be decomposed into a sum of its mean or DC offset, eta, and its randomness, AC power with AC process with zero mean, y. As we discussed in previous slide, the total power would be expectation of its square, expectation of eta plus y square, expectation of eta square plus 2 eta y plus y square. So we can write it as expectation of eta square plus 2 expectation eta y plus expectation of y square. And because eta is a DC offset, we can take it out of expectation formula, which would be 2 eta expectation of y, and we know expectation of y is 0 because it's a zero mean process. So the total formula for the final formula for total power would be expectation of eta square, which is DC power of random process, plus expectation of y square, which is AC power or variance of the random process. Here there is a monumentally important conclusion, and which in fact relates the statistical deviation of a random process to its RMS, and that conclusion is this: random RMS of a random process is exactly the same as standard deviation of a random process when the DC power or when the random process is a zero mean random power with DC power equals to 0. So here again, like what we had for deterministic signals, we've got some examples of RMS values for some random processes. A very useful and practical random process is a Gaussian random process with zero mean, where its PDF is sketched using this bell curve here. It could be shown 66% of realization can be found between minus sigma or a standard deviation to sigma. And as we said before, for a random process with zero mean, the voltage or the RMS value would be exactly as standard deviation of the random process. Another useful example is a uniform PDF with zero mean. So a statistical nature of quantization noise in an ADC or alternatively D2A has got a uniform PDF. So that's why I put this example here, and it's nice to know the RMS of a uniform random process spanning from minus A to A. So again, for a zero mean random process, the voltage RMS or the RMS value equals to its standard deviation, which here is 2a divided by square root of 12. Here we've got two extreme cases of sum of in-phase signals and orthogonal signals. In-phase signals such as these two cosine signals which have got same phase, and orthogonal signals like these cosine and sine signals which have got 90-degree shifted phase. So for in-phase signals, the total RMS would be simply algebraic sum of individual RMS, and the total power is the total RMS square. Here you can see the total RMS is A divided by square root of 2 plus B divided by square root of 2, and the total power is the voltage RMS square. On the other hand, for the orthogonal signals, for the total power, we can simply use algebraic sum for individual powers, and for total RMS, we need to take square root of sum of individual RMS squares. For example, for this example, the total power is sum of individual powers, and the total RMS is a square root of sum of individual RMS square. This is the end of this video. I hope you found it useful, and see you next time.